Okay, so welcome back. We're now going to start looking at the sheet entitled Conduction in Solids, which you should have available on Canvas. To understand electronic devices, we need to understand current and how and why it flows. And so we're now going to go through these notes, and hopefully you'll get a good understanding about conduction and the fact that conduction is really just the flow of charge from one place to another. The charge can be negative, in other words, electrons, or positive, which are holes. And hopefully you're familiar with this concept from stage one. But we're going to revisit some of the ideas just briefly. We can think of where the charge comes from by thinking of solids as being described in two complementary ways. One of those is the bond model, and one of the other ways is the band model. So if we take silicon as our solid and first look at the bond model, the left-hand side here shows the crystal structure of silicon, and the right-hand side shows the bonding arrangement of the atoms in silicon. Silicon's a group 4 element from the periodic table, and it's got 4 electrons in its outer shell. These electrons are used for bonding, and the silicon atoms share these electrons with other silicon atoms. So each silicon atom has 4 nearest neighbours. Okay, so you can see this central atom here is attached to 4 other atoms. And 1 electron is shared with each of the bonds. And this makes the bond arrangement stable. There's 1 associated electron with each bond. But the electrons are not strongly bound to the atom, and that means that when they're given enough energy, for example in the form of heat, the bond can break. This frees the electrons from the atom and enables it to move around the crystal, but it also leaves behind a hole where the bond was broken, and that's where the electron used to be in the bonding arrangement. So that's what those pictures are really showing. If you move down to the band model, you can see that all of these bonding electrons, which are used to bond the silicon atoms together in a crystal, are in the valence band. And we call this EV here on the energy band. This is an energy band diagram. And in the valence band, electrons can't move. Only electrons in the conduction band are able to, up here, are really able to participate in conduction. So the energy they need to get to the conduction band is more than that they have while they're in the valence band. And so they can only get up to the conduction band and generate current, because they can move, if they gain enough energy. And the energy that they need to have has to be sufficient to cross this energy gap. And the amount of energy that is equivalent to the band gap, e.g. it can be considered the same amount as that required to break a bond between atoms in the bond model. So you can see that they're connected. But the band model is useful to understand conduction because you can see straight away that if an electron has vacated the valence band, it's left a hole. And these holes are also then free to move around in the valence band. And it's down here in the valence band where holes can contribute to conduction. And so electrical current is the combination of the electrons in the conduction band moving and holes in the valence band moving. So electrons that have gained enough energy to become free and move around are up here in the conduction band, holes are down here in the valence band, the ones that can move. And we are using silicon as our example because it's the most widely used semiconductor today. But in fact, this same model of the promotion of electrons from the valence to the conduction band can be used for other materials as well, other semiconductors, but metals and insulators too. Now, using the band model, we can also see the importance of this energy gap here, Eg, because it's a measure of how much energy is required for these electrons to be able to move and therefore conduct, to become conduction band electrons, or conduction electrons as they're more frequently known. In fact, in metallic bonding, the band gap, Eg, is 0. So no additional energy is required to generate conduction electrons. And this means that in metals, there's already a very high number of conduction electrons, which explains why metals conduct current so readily. Insulators are in a completely different situation. Their band gap is very, very large. And so it takes a large amount of energy to raise electrons from the valence band of the insulator into the conduction band. And so consequently, there's very few electrons in the conduction band of insulators, and insulators are poor conductors. So, as I said, the energy required to generate conducting electrons is equivalent to this band gap energy. This is measured in electron volts, as we're really talking about quite small amounts of energy. And I've also said that different materials have got different band gaps. And band gaps are one of the material parameters that are listed in your material data sheets on the bottom part. Different materials are listed in different columns. You've got the different semiconductors, germanium, silicon, gallium arsenide, etc. And all of these semiconductors have each got a different band gap, as hopefully you can see and find them now. So these band gaps have an effect on how many carriers are available for conducting current. And it's why I said each semiconductor is different and generates different current and device performance, even when everything else about the device is equal. So if we want to now look at the actual number of electrons available in a metal, an insulator and a conductor, we can do that. We'll use silicon as the semiconductor and silicon dioxide as the insulator because they're commonly used in the fabrication of electronic devices. The band gap of silicon is 1.1 electron volt. The band gap of silicon dioxide is 9 electron volts. And we're going to assume that there's, of course, 0 electron volts as a band gap for the metal. We're going to assume the materials are at room temperature and are intrinsic. That means they have not yet been doped. In other words, they're pure and have the same number of electrons and holes. Because if you remember, an electron is promoted to the conduction band, it leaves behind a hole. So in a pure intrinsic semiconductor, the number of electrons and holes is equal. So we have an expression for calculating the number of electrons and holes in an intrinsic semiconductor. In fact, we give it as an electron density or an electron concentration. And we're going to call it small n here and throughout this module. Okay, so I'm just going to find it. This is the solution that you'll need to copy down. So n is what we'll call the electron density, and it's measured per cubic centimeters and refers to the concentration of free electrons in the material. In other words, the concentration of electrons which are able to conduct current. And so therefore, when we calculate it, a larger value obviously means a bigger current. In this expression, capital NC and NV are the effective densities of states in the conduction and valence bands. And these are the number of states per cubic centimeter at a given energy level which are available for occupation by an electron or hole. And these densities of states are constant for a given material. Again, on your material data sheet on the bottom part, you'll find them, and they're also temperature dependent. As you know, as we've been through, the electron concentration is also highly dependent on the band gap of the material. And this term in the equation here is going to indicate that e to the minus Eg over 2 kBt, where kBt over Q is the thermal voltage and constant for a given temperature. At room temperature, we're going to assume the thermal voltage is 0.026 volts. And this is also on your data sheet on the upper section if you want to have a look at that. There's no need to multiply the Boltzmann constant Kb by the temperature each time. Because some numbers and some constants are very large and some are very small, we often use approximations. So for example, in these calculations of the intrinsic carrier concentration, we're going to assume that the density of states in both the conduction and valence bands are equal to 10 to the 19 per cubic centimetre. So we've got NC is approximately equal to NV, which is approximately equal to 10 to the 19. So that's our expression. We're first of all going to look at the metal. If we put all of these numbers into the equation for electron carrier concentration, with the knowledge that the band gap of a metal is 0, okay, we find that the second term in the equation reduces to 1. That's this bit here. It's going to reduce to 1. And the carrier concentration is therefore around 1 times 10 to the 19 electrons per cubic centimetre. Clearly, that's a very large number. If we then go on to do the same thing for silicon, which has a band gap of 1.1 electron volts, we find that the electron concentration is much smaller, around 4 times 10 to the 10 per cubic centimetre. And please note that this 38.65 here is just the inverse of the thermal voltage, 0.026, and I've assumed that the band gap, in fact, in the calculation is just 1 electron volt. And then finally, if we do the same thing for silicon dioxide, which has got a much larger band gap, 9 electron volts, we find that the carrier concentration of the insulator is 10 to the minus 57 per cubic centimetres. In other words, there are no conducting electrons. And this explains immediately why insulators don't conduct. Instantly, you can see that there's huge differences in band gaps, or rather the smaller, relatively small differences in band gaps, but big in terms of a band gap, generate enormous differences in the carrier concentrations, many orders of magnitude. So you've got 10 to the 19 electrons per cubic centimetre for a metal, none for an insulator, and for a semiconductor, it's somewhere in the middle, around 4 times 10 to the 10 electrons per cubic centimetre. So variations in band gap lead to enormous variations in carrier concentrations, and big variations, therefore, in conductivity. I should say at this point that your data sheet shows the value of silicon, this one here, being 1.45 times 10 to the 10 electrons per cubic centimetre. And this is because of the various approximations used for the densities of states, and also the thermal voltage and band gap. But when the range of electron densities that have been calculated vary so much, whether it's 4 times 10 to the 10 or 1.4 times 10 to the 10, it really doesn't matter. And I certainly recommend that in approximations and calculations, just approximate whenever you can. Just try to get an understanding of the magnitudes that we're really talking about. So once we get an idea of the carrier concentration, N, whether it's big or small, we can get an idea of the conductivity of a material and therefore its resistance, because conductivity, as you can see here, conductivity is obviously related to the carrier concentration by this conductivity equation. Okay, so this is the conductivity equation, equation 1, and you'll see that E is the charge on an electron, that's 1.6 times 10 to the minus 19 coulombs. And N we've calculated is the number of electrons that are available for conduction, and mu is the carrier mobility. Obviously, sigma is the conductivity. But this carrier mobility is another important parameter, and that also varies significantly between the semiconductors. So you can look at that on your data sheet as well now. You'll see that there's a big variation in mobility, and that's really important for conductivity, and because it obviously affects directly what the conductivity value actually is. Physically, the mobility is the ease with which a carrier can move through a material. And in fact, electrons and holes have got very different mobilities from each other, even for the same material, such as silicon. And they're both listed on this sheet, and you can see that in general, electrons have a higher mobility than holes. And this is because holes have got a larger effective mass than electrons, so can't move so easily. So mobility actually arises from, well, it can be given by the equation, it's equal to the charge Q or E, tau over M, we'll call it M star. And the M star here is the effective mass of the carriers, and tau is the time between the scattering collisions experienced by the carriers. And so clearly a larger effective mass is going to lead to a smaller effective mobility. The graph below shows the conductivity values of various materials, and conductivity, remember, is the inverse of resistivity, and so on this graph both conductivity and resistivity are given. Resistivity is at the top, measured in ohms centimetre, while conductivity is at the bottom, measured in Siemens per centimetre. What's interesting is that there's a huge scale in order to fit on the wide range of conductivities for different materials. This goes from 10 to the minus 18 to 10 to the 8. The insulators are grouped at the low conductivity end, as you'd expect. These are on the left-hand side, down here, and different types of insulator provide different types of conductivity. And the best conductors are at the opposite end on the right, up here. And amongst the very best are silver, copper, and aluminium. Now, in theory, they can all be used as the interconnect track for the semiconductor devices to connect the many electronic devices together within the chips. But in the middle range of conductivities are all the semiconductors, where I've just highlighted. And these materials, I believe, are the most interesting. They all have unique properties, and I'm sure you'll have heard of some, if not all of them. There's germanium, silicon, gallium arsenide, gallium phosphide, and cadmium sulfide. They've all got a range of applications, and there's many more semiconductor materials in use today as well. But what I'd really like you to notice is the range of conductivities for each semiconductor. This range for each semiconductor arises because of the special ability to vary the conductivity of the semiconductor, and that's done through a process called doping. Okay, that's only really possible for semiconductor materials. Okay, and there's your labels: insulator, semiconductor, and conductor. Now, doping changes the carrier concentration, and therefore it changes the conductivity of the material, and it has the largest effect on semiconductors. It's the introduction of impurity atoms to the material, which gives rise to either excess electrons or excess holes compared with the number of that you find in intrinsic material. So this means that not only does the carrier concentration and conductivity change, but it's possible to have more electrons than holes or more holes than electrons in the same material. When there are more electrons than holes, we call the material N-type. Remember, N is for negative charges and electrons are negative charges. And when there's more holes, we call the material P-type. P is for positive charges, because remember, holes are positive charge. And without this ability to generate N and P-type material, we wouldn't have integrated circuits, because all semiconductor devices exploit the physics of bringing together the N and P-type materials.